So if hydrogen is traveling 4 times faster than the oxygen, we should be able to answer the following question. If oxygen is traveling at 15 meters per second, how fast is hydrogen going to travel? Well, from our previous calculation, we're able to see that hydrogen travels at 4 times the rate of oxygen, according to Graham's law. So if this is the case, if oxygen is traveling at 15 meters per second and hydrogen travels at 4 times that rate, then obviously the hydrogen is going to be traveling at 60 meters per second. So Graham's law allows us to compare relative rates of gases. Now, one thing we can also do is be given the relative rates at which they travel to each other and calculate a molar mass. Let's say we have the following scenario. What is the molar mass of a gas that takes 3 times longer to effuse than helium? So if we've got an unknown gas that's taking longer to effuse than helium, this means that the other gas is heavier than helium. That is, helium here is traveling faster than the other gas. How much faster? Well, it's traveling 3 times faster. So based on the above statement, we know that helium is traveling at 3 times the rate of the unknown gas. So if we use Graham's law, we can actually put down this relative ratio of 3 to 1. We actually know the molar mass of helium from the periodic table. That's 4. So using Graham's law, we can solve for the molar mass of the second gas. That's our unknown. That is X. So what we know so far is that helium is traveling 3 times faster than the unknown gas. According to Graham's law, the molar mass of the gas on the top part of the left-hand fraction, in this case that's the helium, its molar mass is going to go on the bottom of that right-hand fraction. So we're going to put the molar mass of helium down below. That is the 4. That's known. But the unknown gas, we don't know its molar mass, so that's X. So obviously now we get to solve for X. And algebraically, if you want to get rid of the square root sign, you have to square both sides. So if you square 3, obviously you're going to get 9 out of that. You square the right-hand side, it gets rid of the square root sign. So you'd have X over 4 is equal to 9, or X here would be equal to 36. So square both sides, and then multiply through by 4. So Graham's law allows you, if you know the relative rates of 2 gases, in this case helium to an unknown, we're able to calculate the molar mass of that unknown gas. Let's try one more. We've got an unknown gas that's diffusing at 0.25 times the rate of helium. So what is the molecular mass of the unknown gas? Once again, we're comparing something to helium. And it's telling us that the unknown gas is traveling at 1/4 of the rate. And it's just traveling slower. It's got to be heavier than the helium again. Kind of a different way of stating it from the last problem. We're still comparing to helium, and the unknown gas is still heavier. It's going to be traveling slower. It's only traveling at 1/4 the rate of the unknown gas, or if you will, helium is traveling 4 times faster. So here's how we can visualize this. The unknown gas is traveling at 1/4 the rate of helium. Or another way of saying that is helium is traveling 4 times faster than the unknown. Obviously 0.25 is 25% or 1/4 of something. So the unknown gas is traveling at 1/4 rate of helium, or helium is traveling 4 times faster. So we can set this up very similar to the way we did the last one. We can now put 4 over the unknown gas is equal to, once again, the molar mass of helium is known, that is 4. And solving for X here is just like we did before, taking the square of both sides and then multiplying through by 4 to solve for X. And the molar mass of this gas would be 64. So Graham's law of effusion, or Graham's law of diffusion, allows you to compare the relative rates of gases based on their molar masses. One other way in which you could use Dalton's law, instead of using molar masses of the gases, you could actually use their densities. But most of the time we use just molar masses because they can be added up very quickly if you have a periodic table handy. Now, What happens when you'd like to use the ideal gas law, PV equals nRT, but you don't have the right conditions in order to use it? You may recall from the kinetic molecular theory that molecules, when they travel in a straight line. When they do collide with things, they do have elastic collisions. We consider that the individual molecules that make up this gaseous sample actually have a finite volume, or if you will, they don't have a volume at all, one that we don't have to consider, and that the individual molecules, as they're traveling, they're just not attracted to each other. They're not sticking together, if you will. When they hit each other, they bounce off each other with elastic collisions. And the ideal gas law can be derived from these postulates of the kinetic molecular theory that PV equals nRT. And what's unique is most real gases that we study at most normal conditions, seem to obey the postulates of the kinetic molecular theory, and we really can use PV equals nRT. So if you have a real gas that has high temperatures and low pressures, the ideal gas law is very unique for solving most problems. It allows you to get the pressure of a gas if you know its quantity and the temperature and volume. That is, you can use PV equals nRT. But what happens when you have what are called extreme conditions? What happens when you have low temperatures or you actually have high pressures? That is, can you still use the ideal gas law? And the answer to that question is no. And you have to modify it, and there are several different ways in which you can modify the ideal gas law to account for real gas behavior. That is, real gases, sometimes you have to consider they really don't have a finite volume, that they really do have a volume that must be considered, or that when they do collide with each other, they do interact. That is, they do have attractive forces. And we're going to look at one way to modify the ideal gas law. It's called van der Waals equation. And van der Waals equation accounts for some real gases under what we call extreme conditions. That would be low temperatures and high pressures. Under extreme conditions, you really do have to consider that the individual molecules have a volume, and that, you know what, the individual molecules are attracted to each other. So in your lecture supplement, we're going to be solving an ideal gas law problem, and then look at what the answer would be if we use a modified version of the ideal gas law called van der Waals equation. And van der Waals equation, at first glance, may look a little ominous to you, but it's just a slight modification of the ideal gas law. In order to use van der Waals equation, the equation you see in front of you, you have to have some correction factors. And the correction factors are A and B. And the correction factors A and B are unique for each individual gas that you would like to study. So you actually have to have a table value to use van der Waals equation that provides you with the correct A and B values to substitute into this equation. So whenever you have a certain gas, you have to make sure that you know the A and B values. So they have to be given, or you have to look them up to be able to use this equation. The only time we use this equation is when you have what are called extreme conditions. So if you have extreme conditions and A and B values are provided, then you could actually use van der Waals equation to solve problems. Otherwise, most real gases, pretty much, you can use the ideal gas law, and that's what we're going to be using. But if you have extreme conditions, here's one way that we can go about modifying for the individual molecules really having a volume and really being attracted to each other. So in your lecture supplement on page 25, we're going to do example problem 20. And this problem we're going to work two ways. We're going to use the ideal gas law first. And once we use the ideal gas law, we're going to solve for the pressure. And then we're going to do this exact same problem using the correction factors. That is, I'm going to give you an A and a B value for the gas here in example problem 20 and see what the pressure would be using van der Waals equation. So let's use PV equals nRT here and solve for pressure. And the R value that I'm going to use is going to be the 0.0821, and that has units of liter atmospheres per mole Kelvin. So if we solve for pressure using PV equals nRT, the moles of gas that we have here is the 2.82, and the gas here obviously was ammonia that had a molar mass of 17. So we had to make sure that we change the 48 grams to moles, simply divide by the molar mass. The volume here was given, and it was given in the right units of liters. If it was not in liters, we'd change it. We definitely have to have temperature in Kelvin, so we went ahead and added 273 to the 200 to get the 473 Kelvin. And solving for the pressure here, making sure that we've accounted for all the units, would be 21.9 atmospheres. Now what if we solve this exact same problem and see if we could calculate the pressure if I give you the correction values, if I give you the A and the B value from a table so that we could actually use van der Waals equations. The rest of the information is going to stay the same. The moles of the gas is still 2.82. The volume of the container is still the 5 liters. The temperature of the gas is still the 473 Kelvin. So the only thing we're adding to this will be 2 correction values, the A and B value. And what this corrects for is that the individual molecules, the ammonia molecules, may have to consider their volume of the individual molecules. And also that they might be interacting with each other. And let's see what type of answer we get if we use van der Waals equation. So substituting in what we know with our new correction values, our A value here is going to be 4.17. Once again, I'm getting this straight from a table. You have to have these to use van der Waals equation. The B value is 0.0371. So here we're still trying to solve for P. The N is still the moles. The big V is the volume of the container. And if we plug in everything that we know into this equation, we'll be able to solve for P. It is the only variable, just as we had in PV equals in RT. We're just adding in some correction factors, once again accounting for the individual molecules really do have volumes, and they really might be interacting with each other. So using van der Waals equations and substituting in the values that were provided, you're able to see here that the new pressure using van der Waals equation is 21.0 atmospheres. Using the ideal gas law, it came out to be 21.9. Not a large discrepancy there, only 9/10 away from each other. So as you can see, this temperature here is a fairly high temperature, and this probably would not be considered extreme conditions. So this would not be necessarily a problem where you'd have to use van der Waals equation at all. But as you can see, if you actually use the correction values, you get a little bit more precise of an answer. We're not going to be using van der Waals equation very often for calculating things as it relates to calculating pressures and volumes. Most gases that we're dealing with, we're going to assume that we're not at extreme conditions. Once again, to use this equation, you would have to have a table of correction values. You would have to have the A and the B. But essentially, we just want to highlight here that if you do have extreme conditions, and extreme conditions would be low temperatures and high pressures, you do have to use correction values, like we're using here with van der Waals equations, to get a more precise pressure reading. To finish up today's lesson, we're going to look at some gas law stoichiometry. And in this particular problem you see in front of you, I want you to notice that everything is in the gaseous state. You may recall that when everything is in the gaseous state, you can directly compare, using the coefficients in the balance equations, volume to volume. So since this problem is dealing with all volumes, and we have 20 milliliters of the ammonia and 20 milliliters of the oxygen, we can directly compare those two to make the decision about which one of them is going to be limiting, because the one that is limiting, the one that runs out first, will dictate the amount of product that can be made there. So in this case, if we can directly compare volume to volume, what's going to run out first? Is it going to be the 20 milliliters of ammonia, or is it going to be the 20 milliliters of the oxygen? Well, if you take a look at it, the balance equation says that for every 4 parts ammonia, we need 5 parts oxygen. We need more oxygen than we have of ammonia if we want them to run out simultaneously. Well, that's not the case here. We have equal amounts of ammonia and oxygen. But if we wanted to run out simultaneously, that 4-to-5 ratio says that we would need more oxygen. In this case, if we have equal amounts, the oxygen's got to be limiting. It's going to run out before the ammonia. Based on that 4-to-5 ratio, for every 4 parts ammonia, we need 5 parts oxygen, and we simply don't have more oxygen here. We have the same amount as we do the ammonia. So So the oxygen here is going to be the limiting reactant. It's going to run out first. And when the oxygen runs out, we're going to quit making products. That is, the amount of NO that we can make is totally dictated by the amount of oxygen that we have. So if we want to calculate the amount of product that can be made here for the NO gas, we're going to use the 20 milliliters of oxygen. So if I take that 20 milliliters and I multiply it by 4 and divide it by 5, that is multiply 20 by 4/5, because we can directly compare using the coefficients, we're going volume to volume, we will see here that we're going to be able to make 16 milliliters of that product. So in this case, we took advantage of the fact that we could directly compare volume to volume. This was a limiting reactant problem, but a relatively simple limiting reactant problem because we could directly compare up front to determine our limiting reactant. Once we had that limiting reactant, we could then use that value to predict how much of the product we can make. So once again, 20 times 4/5 was how I obtained the 16. A lot of times we'll be dealing with problems where STP conditions are stated for a gas. Hopefully you recall that 1 mole of any gas at STP conditions at standard temperature and pressure will occupy a volume of 22.4 liters. So to solve this problem, this is a stoichiometric problem, I'd like to know how much oxygen could we make starting with 210 grams of the potassium chlorate. We obviously cannot directly compare using the coefficients of the balanced equation, so we've got to take what's given. We've got to get it into moles. So I need to add up the molar mass of the KClO3 so that I can change the 200 grams to moles. So using the periodic table and adding up the molar mass, we see that's 122.6, 39.1 for the potassium, 35.5 for the chlorine, and each oxygen is worth 16. You add all that up, and of course you get the 122.6. So our first step is to get into moles. Our second step, now that we have moles of the potassium chlorate, is to do the mole-to-mole relationship. That is, for every 2 moles of the KClO3 that we react, we're going to be able to make 3 moles of the O2. So step 2 is doing a mole-to-mole ratio between what you're starting with and whatever it is you're going to. In this case, we're going to the oxygen, so we're going to put that 3 moles on top. We started with the 2 moles of the KClO3, we're going to put that on bottom. So in step 2, we accounted for the 3:2 ratio. For every 2 we start with, we're going to make 3. And because STP conditions are stated, we can now say that for every 1 mole of oxygen that we have, we're going to actually have a volume of 22.4 liters. So if we now multiply through by 22.4, you'll be able to see that the amount of oxygen, theoretically, that we can make, starting with 200 grams of potassium chlorate, is the 57.6 liters. So it's a basic 3-step stoichiometry problem. Take what's given, get it into moles, compare moles, and get it out of moles. This is something that you guys have known how to do for quite a while now. Just re-emphasizing, if STP conditions are stated, you can use that 1 mole of a gas will occupy a volume of 22.4 liters. The final problem that we're going to work is in your lecture supplement. It is problem number 24 on page 26. And what we have here in problem number 24 is we have a solid substance that's a mixture. And in this mixture we have some potassium chlorate and some potassium chloride. We have 2 things, and we're going to heat this mixture and it's going to decompose. Now the potassium chloride part of the mixture, upon heating, nothing happens. But when you heat this mixture, the potassium chlorate part of that mixture does decompose, and it decomposes into the potassium chloride you see in front of you and some oxygen gas. Now the KCl product that we're making here has nothing to do with the original mixture. The original mixture does have some potassium chloride in it, does have some KCl, and the total mass of our mixture, as stated in the problem, is 1.80 grams. But upon heating this mixture, there's only one thing decomposing, and that's the potassium chlorate, the KClO3. The other part of the mixture, the KCl part of the mixture, does not decompose. Now when this decomposes, we're able to collect the oxygen, and notice that we're collecting this oxygen above water. So the pressure that's given here, that 745, is the pressure of the wet gas. When we get ready to do our calculations, we're going to need the pressure of the dry gas. That is, I'm going to have to look up in a table at 25 degrees Celsius what the vapor pressure of water is, because I'm going to have to subtract that from the 745. So we're able to collect 400 milliliters of oxygen at 25 degrees Celsius, and the pressure reading was 745 torr of the wet gas. Using that information about the oxygen and using the ideal gas law, PV equals nRT, I should be able to solve for the quantity of oxygen that was made, for the moles. And PV equals nRT, I should be able to solve for N. If I know the moles of the oxygen that was made, using that balanced equation, I should be able to figure out how many moles of the KClO3 I started with to be able to make that much oxygen, convert that to grams, and compare it to the 1.80 grams of the mixture. So if I have the right information about the oxygen, I should be able to get the quantity of oxygen that was made in moles. If I know the moles of oxygen, I should be able to get the moles of my starting material. By changing that to grams, I compare it to the 1.80, and I'll have the percent of KClO3 of the mixture. And since there's only two things that make up this mixture, if I know the percent of KClO3, by subtracting from 100, I should be able to get the percentage of the KCl that was in that mixture as well. Now, to begin with, first thing we've got to do is we've got to actually find out the moles of the oxygen from the information given. So let's solve. Using PV equals nRT, let's solve for N. And in this case, the R value that I'm going to use is going to be the 0.0821. And it has units of liter atmospheres per mole Kelvin. So in this case, I'm going to have to make sure that volume is changed to liters. Right now it's in milliliters. So I'm going to have to divide that by 1,000. So that's going to become 0.4 liters. That 25 degrees Celsius, I'm going to have to change that to Kelvin. I'm going to have to add 273. So that would be obviously 298 Kelvin. The pressure, I'm going to have to change that to atmospheres. But before I change it to atmospheres, I have to subtract out the vapor pressure of water at 25 degrees, which I'm going to get from a table. So I'm going to say 745 minus the vapor pressure of water. And then to change torr to atmospheres, I'm going to have to divide by 760, because 1 atmosphere equals 760 torr. So if I do all the unit conversions, I'll be able to solve for moles of the oxygen. So notice highlighted in blue, I've subtracted out the vapor pressure of water at 25 degrees from the 745. That would give me the pressure of the gas collected, or sometimes referred to as the pressure of the dry gas. I'm then going to divide that by 760, and that gets me to the atmospheres. Notice I did change the volume to liters, that is the 400 divided by 1,000 is the 0.4 liters. The R value I'm using is the 0.0821, that is liter atmospheres per mole Kelvin, and notice my temperature is in Kelvin. Anytime you solve a gas law problem, you have to express your temperature in Kelvin. So performing the calculation you see in front of you, this will get me the quantity of oxygen that was made in moles. Once I have moles of oxygen, I can then stoichiometrically compare that back to the amount of my starting material. So now that I have moles of oxygen that was produced, I can now set up a mole-to-mole ratio between the amount of oxygen that was made versus the amount of KClO3 I started with. So the balanced equation says for every 3 moles of oxygen that I make, I had to start with 2 moles of the KClO3. So using that balanced equation, for every 3 moles of oxygen that we made, I had to start with 2 moles of the KClO3. And then using the molar mass of the KClO3, I can get the quantity of the starting material in grams. Why do I need that in grams? Well, I'm trying to compare that back to the mass of the mixture, which was the original 1.80. So if you take the 0.0155 and multiply by 2/3, and by the molar mass, 122.6, we find out that theoretically, to make that much oxygen, you had to start with 1.27 grams of KClO3. So that is the part of the mixture of the 1.80. So if we now take the 1.27 and divide it by the total mass of the mixture, we now know that the potassium chlorate was 70.5% of that mixture. And now if you simply subtract that from 100, because there were two components, the potassium chlorate and the potassium chloride, we can now see that the potassium chloride made up 29.5%. And once again, all I did is simply subtract that from 100, because there were only two components to that mixture.